Good morning and warm welcome to one and all for this forum SA India Motion and Control Conference. Uh, I would like to convey my gratitude to the team SA India as well as to ATS team who coordinating this particular event. So today the topic is electronic stability program. So this is one of the emerging technology and the controls which is very much in our automotive industry, and this control system is quite familiar and in exist, and also it's a mandatory in some western countries, but it's going to be mandatory for commercial vehicles right now in India, and it's going to be there in for passenger car as well. So let us know about what is electronic stability programming and what are all the content of this topic today. So this is the content of my presentation. I'm going to speak about the ESP and what are all the types of maneuvers that ESP is required, and what are all the road scenarios, and how to validate through a hardware and loop system, and what are all the integrations of hardware and loop system and its software and the software graphical user interfaces and support models, and the process of validation of ESP, as well as the different types of validation methodologies, and the key parameters of vehicle dynamics that needs to be monitored, and as well as the safety and regulatory requirements that governs the necessity of ESP, and the results correlation, actually the simulation and actual, how it is, how extended it is getting correlated, and how it is beneficial for developing a electronic stability program controller. So, and we end up with this questions. So this is the content. So moving to the presentation. So as I mentioned, the electronic stability programming is a controller that supports the vehicle dynamics whenever the driver loses his control, and in the event of any oversteer or understeer situation in a particular maneuver, that driver could not able to control the vehicle, so the ESP will take over the control of vehicle, and it try to make ensure that the vehicle is in an intended course and to avoid any collision. So main purpose of this electronic stability programming is oversteer and understeer scenarios. Let us listen from
Mr. Anand, I'm sorry to interrupt. I'm
yeah,
sorry to
yeah.
interrupt. Your voice is pretty low. Can you speak
Oh,
closer to the microphone?
yeah.
Thank you.
Is it
Far better.
quite audible?
Absolutely. Thank you.
Yeah. Okay. Yeah. So let us understand the necessity of ESP in from a road event, and what are all the system components in a ESP that supports to take over the vehicle control. So let us oh, the video is not running actually, I don't know.
A situation that occurs frequently. You're driving on the motorway in a vehicle without ESP. In spite of the heavy traffic, the wide road means you can relax behind the wheel. There are no reports of accidents or traffic jams. Suddenly, an obstacle appears in front of you. A sudden steering maneuver to avoid a collision, the vehicle starts to skid and you lose control. The Electronic Stability Program, ESP, monitors the vehicle 25 times a second. If it detects that the car shows a tendency to swerve, the system reacts immediately. Precisely metered braking forces take effect on the individual wheels and return the vehicle to its lane. This is how ESP safely gets the driver out of a dangerous situation.
Okay. This is one of a typical scenario where it happens in the normal driving. So in this scenario, the ESP it's taking over. Actually, we have seen both without ESP and with ESP how the difference is. So what is the how the ESP is controlling?
ESP comprises the following components. A speed sensor on each wheel. The rotation rate sensor measures the car's rotation around its vertical axis. The steering angle sensor registers the driver's steering intention. From the sensor signals, the control unit computes when and how it has to intervene. The hydraulic unit builds up and reduces the braking pressure in the brakes. What happens during the first steering maneuver? The driver has to swerve quickly to the left. The steering angle sensor transmits this to the ESP control unit. But the rotation rate sensor signals that the car is understeering. That is, it's drifting straight ahead towards the obstacle. In split seconds, ESP brakes the left rear wheel, very briefly and sharply. This produces the desired counteracting force so that the car responds as the driver intended. What happens when you react? When you pull the wheel over to keep the car in the left lane after avoiding the obstacle, the car tends to oversteer, and the rear end tends to break away to the left. The torque to the right is higher than the driver wants. In this case, ESP brakes the left front wheel. The torque is reduced. Instead of going into a skid, the car stays on course, thanks to ESP.
Okay. So this is the typical scenario where the ESP is needed. And if you really see, there are various road scenarios occurs. Actually, we need to face that. So where the ESP is really needed. So if you really see that one as spline road, a country road, you can see that one actually a country road or a sharp turn, or this is the kind of a learn change, whatever the previous video, whatever we seen about. So these are all the scenarios where the ESP is needed. So now let us move to how these ESP systems can be validated through a simulated environment. So if you really see that a simulated environment provides us to do a lot of uh, iterations and a lot of combination of trials that we can able to do that. Because if you really see that one conducting this one is physically, yes, there are some standard tests are there, but however experimenting or doing a lot of design of experiments on with the testing maneuvers or the road scenarios is a safety concern. So for that, if you can able to perform it in a simulation environment, and we can have all sorts of combination of the conditions, the environments, which can be validated, the controller is really robust enough to take care of those scenarios. So if you really see here in this uh, uh, the architecture of this the simulation environment, there is a software, the virtual software. uh, Actually here it's mentioned, we have mentioned car maker expect 4, and there is a physical uh, controller, the actual controller which goes into the vehicle. So the simulated environment, within the simulated framework, you will find there is a vehicle model and there is a driver model, road model as well. And these are all in a, software modules which are configured or parameterized for a particular intended maneuvers. And this is the photographs, whatever you're seeing is a typical hardware and loop test facility where you are finding there is a real-time computer and the controller with a test bench where it is mounted on the test bench, and there is a input output uh, uh, module and the power supply module, and put together it's a compact hardware and loop facility which where we can able to do the simulation of the ESP. Yeah. So what is the purpose of hardware and loop facility? So if you really see that one, it supports a significant uh, effort reduced. The effort is get reduced significantly with lot of simulations what we can able to perform through the hardware and loop system. And mainly the it supports to the ADAS and the steering systems, and as well as for the electronic stability programming controllers. The other aspect of the simulation is that it reduces the time tremendously. Actually, if you really see a real testing time, uh, instrumenting a vehicle and conducting a test on a track, and simulating a uh, virtual vehicle in a simulated environment, there is a difference in the time. If you really see that, it's go with that, it's kind of kind of a thumb rule, and which was taken 2 months if it is taking for real time testing, real world testing. So the real time testing will take 2 weeks, and if you are going with the automation, so further it can reduce into that. Actually the results can be get, but however there is a accuracy and there are certain percentage of correlations are needs to be compromised. Still there is a debate and the questions on the correlation part. But however, it some there's a substantial percentage of results can be taken into the consideration. Coming to the HIL integration, whatever the earlier in the earlier slide, I was shown the block diagram. This is a typical integration of a car maker HIL system, where you will find there is a software module which is a car maker and which has got a IPG road, IPG driver, IPG tire, and IPG car, and which needs to be parameters. And there is a GUI for in the host PC to access the model and the for the analysis. And this whatever systems are mentioned in gray are the physical systems, the ABS and ESP ECU, and it has two interfaces. One is the CAN, communicate via CAN, and another one is via hardwired. And if you really see, there are certain sensor models which are all are available. We can able to do it through a software models as well as a physical model. So this is how typical HIL, and currently if it's for the ABS and ESP, mainly the controller, the system integration is looks like this. And nowadays the ESP is along with the EPB, electronic parking brake system, which is are there, so which also can be integrated in the system for the assessment of effective parking brake system. This is the GUI, graphical user interface, where there are various inputs are required to be fed into the system to create the model and create the environment to conduct a simulation. So we need the input. There is the main thing is how extend the accuracy we are having in the input, that much accuracy of simulation outputs we can gain. So it is more important that the each and every physical parameters are to be taken in consideration, and the vehicle parameters, mainly the kinematics and compliances and tire models, these are all very key elements that needs to be programmed in such a way so that the simulation will be very accurate. We have a fail-safe tester where we can simulate a fail-safe conditions, vehicle fail-safe conditions, both electrical and mechanical, and we could able to assess the vehicle in a virtual environment. As I said, there are other models like tire there, which are all the key elements of the simulation, because this contributes a lot, because this is having the creates that environment. So the environment needs to be created, because if you really see that in a vehicle model we have a lot of design parameters, and which can be quantifiable, and it is a objective values which can be fed into that, and the environmental things are needs to be taken into the consideration, but the conversion accuracy is very important. If you really see that the tire model is very important for this simulation, especially for electronic stability controller, the tire model is needs to be more accurate. Currently I can say globally, the TireDex is the that is Tire Data Exchange, is a kind of consortium who generates the data of the standard tire models, which is said more accurate. If we can actually it captures the most of the aspects of the tire. So I can say that one this is the one of the best model globally. Everyone is using it, and the other aspect is the road. The road model is very also other vertical, I can say that one. This is very important, because the altitudes and longitudes and the lateral inclinations, everything, these all parameters are very important. Currently the models are such a way sophisticated, like we can convert the Google map. Actually, if a particular um, uh, a track or a particular uh, city driving conditions, so we can very well take out the pattern of that particular road, and we can able to convert it, so that there we have some sophistication, we can have more accuracy in the road simulation. So that is also one of the important aspect. And coming to the next model is the driver model. So the driver behavior is very important, because if you really see, there are it, it is categorized into three, but however we can go with more and more customer usage pattern and the driving pattern, we can create the driver characteristics. If you really see, as of now, the major three major categories are defensive drivers, normal driver, and aggressive driver. So this is a typical pattern. What it is derived by IPG from the inputs of 500 customer, and you say, and their way of driving. Okay, so from that the characteristics are defined. Okay, so that's all about the modeling of vehicle and the environment in a virtual uh, in a virtual environment uh, for using a hardware and loop testing. And this is the typical V model of a hardware and loop. What are all the key aspect of this is, if you really see that there are levels of testing. If you really see that one, the levels are defined with respect to the maturity of the model. So the if you really see that we cannot develop the model in a quick span of time. Actually, it needs a maturity, it needs a lot of accuracy. Each and every aggregates needs to be parameterized, taking from a steering system, a brake system, or a suspension system, and the chassis. So it needs a lot of critical parameterization. So it will be developed over the time. So if you really see that one, integrating the hardware, before integrating the hardware of electronic stability, first we need to prove that the vehicle model which is going to be tested in a virtual environment is accurate, or it's up to the mark. So if it has some sort of lacunas, then there will be a it will cause the deviation in the results. So to avoid that, so if you really see level 0, level 1, level 2, if you really see up to this, the characterization and the parameterization of the vehicle model, this will happen in only in software and loop level. So it uh, within the software, that means using the IPG's carmaker GUIs. So we define the parameters and we could able to develop the model. And once we run it in the simulated environment, uh, we need to confirm that vehicle model. Once it is confirmed, then we need to integrate the actual controller and how this controller is uh, um, uh, performing in that virtual environment with this vehicle. So this will go into the level 3, level 4, and level 5 testing of hardware and loop. Actually, level 5 is mainly for the fail-safe testing, and which will be performed. So what are all the testings that performed in a virtual environment? If you really see that there are standards that provided the electronic stability programming to be tested in the tested. So if you really see that ISO lane change is one of the typical test requirements. Lane change, a single lane change or double lane change will be one of the uh, requirement as per ISO 3888 standard. And also the slalom 80 meter and the 36 meter, it's a kind of stability control test needs to be performed. So if whatever you are seeing here, the green color is the vehicle pattern of movement. If you really see that one, there are the pylons are kept at a distance of 18 meter, and between that the vehicle has to be passed through. So if during that uh, maneuver, the stability, how it is, the parameters are monitored. And the next typical test is the steady state circle. So the 40 meter and 100 meter stability is a continuous steady state circle. The vehicle will be driven in a in a defined radius of circle, and see that whether at what point of time the vehicle is losing its stability. The another test is the sinusoidal and pulse input test. So it's just a kind of a steering input will be given by the driver, and he will check that whether the vehicle is having susceptible for that event or not. A similar way, the steering input is a sudden pulse, a sudden jerk will be mean to say that the angle, steering angle will be changed in a particular time to see that whether the vehicle is having any sort of uh, um, instability. Coming to this next um, test, if you really see that the lateral force test, this is as per ISO 7401 standard. So mainly this is for step input or a jar turn or a single cycle sinusoidal or a pulse steer or continuous sinusoidal and random input. These are all the tests or helps to understand the lateral force, how extent that the vehicle is getting controlled in a lateral force. And there is a obstacle avoidance test as per ISO 3888 is there, and the consumer unions short course also there. This is also the typical similar to the previous one. There is a course down test is there as per ISO. It is typically a downhill testing either as per IS 14785 or SAJ 2452. This defines the standard for the ESP testing as well. These are all the key parameters that needs to be monitored and assessed, and the control needs to be there to ensure the vehicle stability. So mainly vehicle speed at a vehicle by intended vehicle speed, steering wheel input, wheel forces, yaw rate, slip angle, roll angle, lateral force, lateral accelerations. So these parameters are to be monitored in this test and assess the stability control. Coming to the safety and regulatory requirements. So these are all the global governance where they uh, provide the regulatory requirements which is applicable for in their country, and quite some other countries also adapting the same. Actually, this is a kind of it's derived from the US uh, FMVSS standard or this TAP 14848 Canada standard. Actually, they are the forefronters. They defined a lot of standards and established, and they put in as a regulatory requirement as well. So which is emerging right now. So which is followed, and it is there in AS 0998, which is one of the standard which talks about the uh, uh, stability control and other thing. And one of the typical European standard is ECR 13H, so which is mainly for electronic stability programming validation only. So with this, the glimpses of uh, whatever we have seen, the setups of hardware and loop, and how extent the simulation helps helps in the development. If you really see that one, to perform an actual validation or actual testing, it needs a lot of effort and a lot of time and money. Because if you really see that the actual test results always, because it's on the live environment, so it gives more accurate. But however, nowadays the simulations are more effective and it is accurate, that we can get a very better results, and which is close to the actual. This is the typical example, whatever you are seeing it. If you really see in a braking environment, normal braking, whatever the pink graph, whatever you are seeing is the actual, and the whatever the navy blue, whatever the line you are seeing is the virtual. So if you really see that one, there is a little bit of uh, uh, gap in it, because that can be overcome by the making the model very accurate. So that's how this the simulation is helping. But if you really see that the correlation, I can say it is more than 90%. So that much of effort to take a design decision is really uh, helping the development of the OEMs, and it's further growing, and we are exploring for other uh, uh, upcoming technologies as well. With that, I hope I have clarified about the ESP and what are all the testing methods, as well as the uh, what are the key aspects and the correlations of those things. Thank you listening to my presentation. Over to the uh, Devanshu. Yeah, thank you.
Thank you so much, Mr. Anand, for such an insightful presentation. There are a few questions from the audience.
Yeah, please.
First question is from Mr. Prashant Shukla. He wants to know, is there any change in vehicle dynamic testing in conventional car and in level 5 ADAS vehicle?
Conventional car in an ADAS vehicle.
Yeah.
Yeah, actually, see, if you really see, there is a change is definitely is going to be there. But currently, if you really see that one ADAS vehicle in European market, there are a lot of validations are happening. Actually, the standards are getting amended, and which can be published soon. Actually, maybe we need to take a watch on that. Yes, yeah. I hope this answers the question. Yeah.
Okay. Mr. Sachin Dhete wants to know which method gives accurate results, HIL or SIL or actual testing?
Accurate result, absolutely actual results. That means actual vehicle testing only. The only difference that what is the necessity of going for a HIL is that we can able to very close to the actual testing, which helps in reducing a lot of effort. Time is very important. Actually, everyone is working for the time, because how fast we need to get into the market. So development time needs to be reduced. Actually, in that, for that actually HIL is supporting a lot. But if you really see that one accurate result, 100% accurate result, yes, absolutely, it's actual only. But with compared to SIL and HIL is better. Actually, currently there are systems are kind like DIL. GIL is come. Now it's the DIL. HIL, the one step ahead is the DIL, driver in loop. Actually, that is very close to the actual testing. Actually, where the instead of a simulated driver or using a driver characteristics, we are using an actual driver itself. So there the accuracy is much better than HIL also. So yeah, I hope that answers the question.
Yeah. His follow-up question is how the vehicle improvement is shown on actual vehicle with ESP module.
Come again. Sorry, I come again.
Yeah, he wants to know how the vehicle improvement is shown on the actual vehicle with ESP module.
Okay, actually improvement in the sense, if you really see that when see ESP is meant for a particular to take a control in a particular scenario only. It will not be in every aspect. Actually, it is not a it is for a event or a safety controller. Whenever that particular scenario occurs, this will take over the control. That time definitely the performance will be seen or realized by the customer, actually the driver or whomsoever, because the performance of the ESP will be in a stability control whenever he is having a highway drive, or sometimes in a city drive out as well, if wherever a short curve or something, you need to have a spline kind of thing. So definitely it supports it, it assists the driver. So that is the only way we can realize its benefit. Yeah.
So Mr. S. Mohan wants to know what is the scope of using both ESP and ABC under emergency hard braking with lane change? And how will further braking be possible under ABS pre-activation for ESP control to keep lane change with full braking? Mr. Anand, should I repeat the question?
Hello.
Mr. Anand, would you want me to repeat the question?
Yeah. I lost your because
Yeah.
some
So Mr.
interruption.
S.
Sorry.
Yeah. So Mr. S1 wants to know what is the scope of using both ESP and ABS under emergency hard braking with lane change? And how will further braking be possible under ABS pre-activation for ESP control to keep lane change with full braking?
Okay. First of all, actually, the ABS and ESP, if you really see, both are for different purpose. Actually, ABS is mainly meant for the anti-skidding, and if you really see that the traction control is another one aspect added to the ABS, which normally supports for the traction control. So ESP is use the ABS system. Actually, there is no separate controller is required, because the components whatever is needed for the ESP and ABS are more or less same, with the additional valves, only with the additional similar valves. Same, actually, not this. If you really see that one, ABS have 8 valves. Actually, for going with the ESP, we need in hydraulics some 12 valves. Actually, intended control which needs to be take over by the ESP during the event of loss of stability. So that time it sends based on the inputs from the steering and the yaw rate. This will take the decision. Actually, it's a artificial intelligence sitting in it, which will take a decision and apply the lock the particular wheel without a driver intervention. That means the driver may tend to apply, but if you really see the one, he can try to slow down, but whether it is sufficient or not, with respect to the course whatever the vehicle in, so the ESP will take over the control. For that moment, the ESP will take over the control, and it will ensure that the vehicle is in the course. So if you really see that one, the braking and the lane change, which is happening during that time, the ABS will be kept for a moment, and the ESP will take over. If you really see, this happens in a fraction of second, and that particular at a higher dynamic speed, if you really see that one, the vehicle inertia also to be that much extend. So the time and the reactions are very important to take this control for in a millisecond, and it will ensure that the safety of the vehicle. So I think uh, uh, the 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 ABS system and the ESP is doesn't conflict. Actually, it goes hand in hand. But however, for a particular span of time, this ESP logic will come into the picture and ensure that locking of the wheel and ensure the vehicle in a intended course. Yeah, I hope this answers the question.
Thank you so much, Mr. Anand. In the interest of time, this would be our last question. Now, I would like to invite Professor Bernhard Sheikh. He is the CEO of MdynamiX AG and Research Professorship, University of Applied Sciences. He is involved with the vehicle dynamics and automated driving. He was the test and development writer for tire, bike, and suspension companies like Dunlop, Pirelli, Ducati, White Power, Öhlins, etc. Over to you, Mr. Professor Bernhard.
Good morning, everybody from Germany. First, I would like to start the presentation. I hope it works, and share my presentation for all. So, do you see my presentation? Maybe I have to stop again and.
Yes, no, not yet.
Okay, I have to share again because I need to also to enable the audio format because I have integrated some movies. Okay, now you should see my
Yes, that's correct. Yes, we can see that.
Okay, thank you very much. So thank you very much to have the opportunity to give a brief presentation about our activity of advanced driving simulator for vehicle dynamics and others, advanced driver systems or automated driving evaluation, and our research. My presentation is structured in following topics. First, I would like to give, I would say, brief introduction of our institute for driver assistance and connected mobility to see where we are embedded in which research environment. I can also give a brief introduction of MdynamiX, but it's just brief, and the core of my presentation is to give you more insights about our highly dynamic driving simulator, and first of all the methods and applications we conduct on this driving simulator, and for vehicle dynamics and others, and then we can have discussion. And I would like to give you also deep insights about the current status, what we are, and I have also with me, I would say, several validation results and comparison, road testing and driver simulating testing. So first, I would like to give a brief overview of our institute, the Institute of Advanced Driver Systems and Connect Mobility is a research institution of the University of Applied Science in Kempten. They have a brand new building on a test site nearby the Memmingen Airport. And the test site is in use, I would say, of about 50% of the company Continental. So the test and validation activities around ADAS AD from Continental are mainly conducted here at this test site. And here, I would say, a new campus, or you can say a technology campus, was started to develop several years ago, and our building is in that area, so we have direct access to the proving ground. Beside that, we have some other interesting company, with the company MIMechE Automotive, the son of the CEO, the former CEO and chair Ferdinand Piech start a high-performance electric car development, and the development center will locate it here, and they're still in our building. And we would say also some other innovation partners will come to our building. And the company MdynamiX, which is an affiliate institution with also around about 25-30 people, also has bought this landscape and will start and construct their headquarter in that area. So this is I think, an interesting environment. University has about 50% of this building over all floors. The first is we have the workshops and laboratory, and also here is located the driving simulator. The first floor we have HIL laboratories, sensor laboratories, and then we have 2 floors with project rooms. We have around about 100 researcher for research group, which are more located or more oriented for automated driving, safety, sensor, and connect. And I'm responsible for the institute at all, but additionally for the research group A-Drive, which is splitted and structured in human factors, vehicle testing, simulation, artificial intelligence, data science, and software and function. And A-Drive is the biggest research group with around about 65 to 70 people. So at all, they are 7 professors. And one of the core, and this leads also to, I think, to the driving simulator, is that we have two main targets where we identify our research questions. On one hand, we work to, would say, or we like to improve the development efficiency, how we can bring simulation and testing together. This is I think a big issue, and the driving simulator plays a big role, because if we imagine that we have maybe in many years no prototypes at all, we need any instance where we can experience the functions and behavior of vehicles before we bring that into to bring that onto the road. And therefore a driving simulator plays a big role, because we cannot simulate everything, and maybe we have no cars to test that, and we would like to front load. And this is just one, but we see there are also big gaps in many cases, and therefore our research and our projects are focused to bring that together. And another important issue for us is how we transfer from fun to drive to fun to be driven, how people will experience the driving behavior of future vehicles. And the first impression seemed to be that it's not so linked so hard, these two questions, but these are linked very hard, because even if we have no prototype, we need here the capability to, I think, to estimate and to simulate the driving experience in the early stage of the development. And therefore this plays a big role at all. And in both cases, and driving simulator is needed. To give you the first impression how our driving simulator looks like, I have a short movie just to give you, and I will explain that more in deep. This was our, I think, test facility in Kempten. Now the driving simulator is moved to Memmingen, is built there much bigger. And but just to give you an impression how the simulator works and what are the key features of such a simulator. So the simulator came off the Formula One, was developed by McLaren and hand over to Williams Formula One. And today 3 Formula One teams use the same concept of a driving simulator. It's McLaren, Williams, and Alfa Romeo. Sauber, you can say it was a Sauber. And the driving simulator brings us, let's say, big potential and guarantees a high dynamic, which we don't have found in any other driving simulator. This was the reason why we decided for that and start a cooperation with MdynamiX at all. So you see the mechanism and the motion of the platform. So we have 6 degrees of freedom where we actuate with about 8 actuators on a linear system. And as you see, this is a very dynamic, low latence time, and especially for vehicle dynamics and there, especially for the on-center behavior and steering response behavior, it brings us a fantastic dynamic and agility. And we have up to 50 Hertz, depends on an axle, but I will show you later on some samples. So we have a certain motion room, and compared with a hexapod, our motion room is much bigger, and so in general we have 2.5 meter, but this is the effective motion room. Some simulator gives a theoretical motion room which we cannot address, but in our case we have a effective motion of 2.5 meter, which will be extended now for further 400 millimeters, so we come round about to 3 meters. And beside that, we have a high sophisticated environment simulation from RF Pro. And I have to say that this presentation was done together because we have for the driving simulator and I would say technical partnership with certain companies like ABD, MdynamiX, with COSIN, with F-Tire, IPG, and RF Pro, because such a system has a certain complexity, and therefore it's important that all stakeholder interest to generate or to develop new methods and new technology on the driving simulator. So, but one of the core is also our environment simulation, where we have also nice models from cities, from cross-country roads, etc. I will come there more in deep. And we selected the newest Baco projectors, 8 projectors with up to 240 Hertz. We realized in our test environment in Kempten that 120 Hertz is too less, and it's stressed the driver, and due to the 240 Hertz, we could improve I think the workload of a driver, of a test driver, significant, and got a much better feedback. And because we have the case that a test driver is sitting, for example, 8 hours in a driving simulator, and this is a big stress, and therefore I think this was also something what was important. It also influences the motion sickness and all this stuff. But now we have a brilliant, a very brilliant projection system. And but as I said, this is also very has a certain complexity. Just to give you some impression here, how it looks like. I think this is a simulation in Paris. So we create there certain digital twins, which we transferred to the driving simulator. To give you an impression of what the motion platform can do, I have here a comparison with a real test drive and a drive on driving simulator. And what you see in a ISO slalom, we saw in the presentation before certain driving maneuvers, and one of that was also the slalom. And what you see that the motion room, I would say, is adaptable, so we can move the platform within a slalom completely. So we don't need a certain queuing, maybe to give a G response from or something else. So we can do everything in that case out of our rail system, and with a new extension, so we can run a slalom completely out of the rail system, and this gives a big opportunity if you can simulate one-to-one the body motion to a driving simulator in certain use case. It's clear so far that it ends up, if you make a 90 degrees turn or something else, then it ends up in a certain time. But you will see in our use case that we are focused on certain use case where we have a big strength of driving simulator. What was unique and what we realized in a very early stage is, I personally have driven more or less, I wouldn't say every driving simulator, but a lot of driving simulator, and I can tell I have never got a steering feeling what I expected from a car. And everybody worked very hard to make by model order software the loop with an actuator, but I would say everybody failed to simulate a realistic driving feeling or steering feeling. The reason is the steering system is very complex. The ECU behavior, the sensor behavior, the mechanical behavior, all this stuff to bring together is, from a numerical part, a big issue. And on other hand, at the end of the day, you have always the question, is that the realistic steering feeling? And therefore, we came up very early with the idea to miniaturize and steering test bench. You know, Professor Pfeffer in Munich is, I would say a kind of godfather of the steering, and he also developed methods for steering. And together with him, we developed in the company MdynamiX, I would say, a very small and light version of a steering actuator where we can integrate the complete steering, and this brings us a complete new level for steering feeling, and makes on other hand steering application and steering evaluation on the real steering with the real ECU, etc. possible. And this was a very important development. I have this module here. I have also a movie in YouTube, but I will skip that. This is the actuator, and the big issue was it should be very light, because we have to be very careful about the light to I think to keep the dynamic of the platform. So steering module can be integrated here. You see here this is a steering column. We drive with a real steering column to the steering system. Then we have here a mounting plate where we connect the steering actuator with the steering system. In that case, it's a APA, but so we can then with a frame system, we can change the steering in few minutes, and we can also switch between a rotational actuator directly on the column to a linear actuator to the overall steering system in few minutes. And also we are able to adjust the system that we have the same position of the vehicle, and this makes things very effective. But I will show you the use cases later on. So to give you an impression of our use cases, we realized that you can, at the beginning, if you make a table, what you can do on a driving simulator, you will have a big mind map. But at the end of the day, if you would like to optimize the system to this big mindmap, you realize that you can do everything but nothing. And we start to develop our driving and select our technology use case basis. So we define what we would like to do and where we see big needs. And then we start with 2 activities, was vehicle dynamics and others. And then step by step, we identify use case, test the use case, optimize things, and work together with the real test driver on this use case. And at the moment, we would say focus on following use case. We have steering calibration. This is one of the biggest use case because we can integrate real steering system. We'll show that. We have suspension setups or also suspension concepts, also complete vehicle concepts can be driven there. Tire development is very interesting. Controllability in failure case, which is also I will show. And also we start to work with chassis control setups, and this is I think more on vehicle dynamic side. Every day we have new ideas, but to be focused, I think this is our main focus. We do also some other things. Another topic is ADAS AD. This is not so easy in many cases, but what we realize is that the lateral dynamics means the lane keeping assistance system, or lane keeping, or for example, active lane departure warning, etc., could be applied there. We have also done first test, and it's very, very interesting use case to also to apply or to calibrate the system on a driving simulator. But there are some other things, and other important research is how is the comfort present, which comfort and which systems do you need to drive an automated vehicle. So it means the question is which comfort people are expecting in the future and need maybe to conduct certain secondary tasks like reading or working or something else. And this is difficult to investigate on the road and could be done there. Very nice. There's also some HMI issues, etc. But these are our main use cases. To give you also some impression, we have done also some validation. Also, always the question is, does the driving simulator behave similar to the vehicle? And this is always a question, and it's clear so far. We have at all driving simulators we have certain limits for the motion. In some very big one we have less limits, but then we have a big weights and big inertias, which leads to limits in a response behavior, and maybe also different vibration and so on. So yeah, every simulator has some strengths and weaknesses, and you have to select which tool for the right application. What we have done is we have done a lot of typical vehicle dynamics driving tests, like slowly increase steer, slalom, iso lane change, sine with dwell, and all this stuff, and just to check whether the simulator behaves similar and also the driver behaves similar. And we was amazed that on subjective level as an objective level, the driver said that we have a very close behavior. Even they have to, I think, filter out certain effects or maybe adapt to certain things. But the test driver behave on a driving simulator in terms of vehicle dynamics very, very close. And this was a very good news for us, and leads also to maybe to certain things. Just a comparison simulator to real driving in that case. So always the question, if the driver drives different in the driving simulator and the vehicle behaves different, then maybe the question could be answered, maybe not correctly. But we see that we came up with a very close behavior. And this was very good news. You see also the steering input is very similar, and all people who know if you drive 10 times and driving and slalom, you have 10 times different results. And with closed loop driver, but what we see, we have driven that with experienced and unexperienced driver. We have a very close behavior in that range of use case. No? Maybe that's not valid for every driving simulator, but our focus was always we would like to have that in a certain range for our use cases. Also from gradients, side slip gradients, or also from the behavior from weave test behavior, steering angle to yaw rate, we see this is quite similar. And I think the difference is not bigger if the repeatability difference between the tests. So to give you some insights, I think that would be right now more excited for you what we are doing. I would say one of the top application is the tire testing. We for that case we have we have a very good validated vehicle model of vehicle models of different cars. We got the tire models from a tire manufacturer, mainly in Pachega, but I will come up with F-Tire as well. And so we can apply different tires and it can quickly change, and we can test that in a kind of blind test with a test driver. And we had many test drivers from OEMs and tire suppliers to test that. And a typical use case is one-sender behavior, or they called it two-phase behavior, or steer increase behavior. So they just work on a straight, and the good thing is you can do that with a 20, 40, 100 kilometer long straight, and can test that very concentrated. You can also eliminate maybe a certain roll behavior. Some test drivers said, I would like to reduce roll behavior to be able to focus more on a yaw behavior, to see how is the turn inability or the steering response of a certain tire. And it was amazed for us that test driver can identify free released tire on a production vehicle just in a 0.5 rate difference in a right order. And this was very interesting for us. And they can also select tires which is not releasable and which are releasable. So we came to the conclusion tire testing is possible. There are many disciplines for that. And what we do here in parallel, we have developed a nice app that the test driver can do the evaluation directly in the car, and in parallel we can also analyze the tests in objective way. So this is a typical setup for tire testing. So we can also mix up in the virtual environment subjective and objective testing. Another interesting use case is steering. Steering, as I said, we can integrate a complete steering system, and did that also with multiple steering calibration engineers. They do normally, as the tire tester, they do normally the job on a real road, and they are interesting to shift their calibration task to the driving simulator, because the motivation is clear. Even they get the prototype very late, and if they start, they need certain time until they reached a certain level of a steering, and this needs, I think, weeks and months. And they would like, but the steering system is available very early in the development, at least a half a year, or the steering system is often an carry over or slightly adaptive part from other vehicle type, and therefore they are able to integrate that. And they here on on a ECU, they can directly calibrate with Canapé, Inca, or however. Via XCP, they have access to the ECU, and then they can calibrate directly on a cone. There is no doubt, there is no discussion. This is exactly the steering which you can integrate to the test vehicle later on. Exactly the same component, and therefore they really like and are very keen to do that. And so they can also test maybe steering systems from different suppliers, because often the case that they have for different vehicle variants or derivatives, they have different systems. For the Golf 7, for example, they have a dual pinion and an APA, depends on a derivative. So they can also maybe compare. In some cases, they have steering systems from Bosch and maybe from however, from TRW or from ZF. So therefore, they are quickly able to do that. And interesting is that they can calibrate directly on a system. The use case looks very difficult. I would say the main time what they need is out of the on-sender behavior, and also to see how the steering responds on that. But what is also we say in German Rücklauf, it means the back turning of the steering and so on. And they work also often on long straights, and therefore they can do, I think, what they said is, would say the most time what this is doing on a straight behavior, and looking for the application. And here we can feel that very detailed, and can apply the steering system. And I would say in the same case, we have the app inside for the evaluation. Basically, the test driver communicates with another engineer, which have always access and monitor access to the ECU and monitor the the test plan, the conduction of the test plan. And often the case, after they are finished on a straight road, then they go to another maneuver. Some maneuvers are for example slalom or isolate change, or also steady circular driving or something else. And also the next step is to go to an I will repeat that, maybe to a cross-country road. We have certain cross-country road which are one-to-one digital twins of real roads, and therefore you see also the movement of the body, of the motion. Therefore, we can also test, I would say, the behavior of steering then under realistic conditions out of a proving ground. Another interesting use case is the controllability in failure case. I would say this is cooperation with Volkswagen, I can say, because we have done 2 publications for that. They have always the question, even if a certain part fail, does the driver recognize that? And is the car controllable? And this is difficult to test under real condition. On one hand, it's dangerous for the test driver, and on the other hand, this is not holistic enough. You can just pick out maybe certain cases, and then they pre-damaged a certain component and hope that they will, I think, break in the right moment, and therefore the motivation is high because if they have just question or cases, they have to react immediately. And if we can do that on a driving simulator, is a big win for them. Here we have such a component. It's just a sample. In Excel, you can imagine there are many components which can lead to structural errors or structural failures. And what we have done is we have transfer the failure behavior by a simplified, you can say, wheel behavior model to CarMaker, and so we can then imprint this error to the certain wheel in, I think, time behavior and I think under transient, static and transient condition, and can bring the error in defined use cases or defined driving conditions, and have a look how the driver can control that, and what are the limits that the driver is not possible to control that. I would say the same loop. We always do objective measurement with our tool MX-Eval, where we can objectivize automatically the data, and we have always an app inside to test that, just to see that. So we can imprint maybe in the corner or in a turn situation, however, the certain errors, and then to see, does the driver control that. Therefore, we have done a lot of investigations and research how they work together, because always the question is, does the simulator I think is the simulator capable to test controllability behavior? Therefore, we start a certain validation project. So on one hand, we simulate the different failure cases in Adams and transport that to CarMaker. On the other hand, we test some of those use cases out of the FMEA table on the real vehicle, and did testing always with subjective and objective evaluation of subjects. In a subject study, part of the subjects was expert and a part was not non-experts, and we did the same test in the driving simulator to see whether the controllability can be simulated on a driving simulator. And what came out is the driving simulator is it's a little bit more difficult to control the car on a driving simulator as on the real vehicle. And this is a good news, because then we are on a safe side. So even if the vehicle is controllable on a driving simulator, the probability that the car is controllable on the real vehicle is very high. And this is a research which is ongoing. The first part was done this year, and we will start next year with some other cases, error cases, and with a wider bench of subject, but looks pretty good. And we also found certain correlations, for example, for controllability rating and side slip gradient. So a side slip gradient is one of the key, but we have found many other interesting values, and this leads also to the chance also to do some pre-simulation, for example, in CarMaker, to identify whether an error can lead to a certain uncontrollable situation. So coming up to the next use case, and this is one of the amazed use case, because we found that the platform has a very high dynamic, and even if you drive, you feel this is a very smooth behavior, and it really feels like in a real car, in the vertical dynamics and the lateral shake and all this stuff. And we came to the conclusion that the comfort evaluation must be a very interesting topic. And what we did is we integrate 3D models like OpenCRG, for example, 3D models. We integrate F-Tire, and you know F-Tire is a very detailed tire model, physical tire model, which needs a lot of calculation power. And in the meanwhile, F-Tire can be run in real time, but you need a high performance machine like a concurrent, where you distribute your different tires on different cores and connect that with a vehicle model. In our case, we connect that for the first test with CarMaker, but we have also a version where we connect that with a multi-body model from Simpec with a about 100 or 120 or however degree of freedom, and to calculate the vehicle motion. So we run over uneven road, and the vehicle motion are calculated. We'll send to our motion system, and the motion system communicate with the visualization, with the environment system, and therefore the driver feels that. We did also a lot of measurement to measure the body motion, to see which frequency and all this stuff we can generate. So, and therefore we have different use cases. Just to show you such a sample, this is a road nearby to the Nürburgring. It's called Kempten, uneven road, which was scanned in 3D. See a certain behavior of the car. You see also the roll, the pitch, and the primary right, secondary right behavior. And as said, not all evaluation can be done in an objective way. So we can do some objectivation, but I would say the little things are somehow important. And we have 3 options to do. We can drive on 3D roads. We can also drive via certain single events like leads or something else. But we have there 3 interesting options. One option is we can simulate. We can do a pre-simulation, for example, in Adams, and then we can replay that on a driving simulator. We can do the same for vehicle testing. So we can measure a real car, let's say a benchmark vehicle, and then we can run that on a driving simulator. Exactly. We can also blend out maybe a certain frequency if needed, and then we can run that on a real driving simulator. And we can run in a closed loop with a vehicle model, and then we can compare that. So we can compare real measurement of a benchmarking, which we cannot simulate in a car because we cannot set up the complete model with all stuff, necessary stuff, and therefore we can then transport the benchmark to a driving simulator, compare with our model, and see always the maturity level. And even if we have not enough calculation power, or the detailed model of detail is not enough for the vehicle model, we can do that also with Adams or SIMPEC or DATS simulation, and then can compare that. Just to give you an impression, this is a redrive profile. You see, would say the behavior. In that case, it was an investigation where we check which comfort for an autonomous driving condition is necessary, and what does the people say when they cannot conduct, and they would not like to conduct certain points. To give you more insight, I have I think also a movie from Paris to see that. It was filmed by me. So this is a real 3D road in Paris, scanned by a laser scanner. And with the F tire, it's a complete different behavior. You know, and Pacheco is a point contact model, and an F tire has a grid and is a complete physical model, and the behavior is a complete different. And then I think show you a movie. Maybe it explains it more. It's, I would say, a movie which we did together with those partners. So we have, I would say, this is a proving ground in Milburg, which is also detailed in a grid, in a detailed grid, and the F tire running over this uneven pavement, and together with the vehicle model, we can then simulate the vehicle motion, and it's amazing how it feels there, and you get all the vibrations, etc. in the certain cockpit, and see here also the movement. This, I would say, this is also a 3D road. Yeah, and to do that, we are on the way to digitalize two labs nearby our research site. One is so-called the vehicle dynamics and more for steering evaluation, for handling, or there are also some parts for comfort, but it's mainly more for handling. And we have here a very nice part for comfort road where we have, it's amazing how compressed in a short loop we have, I would say, different excitations for the vehicle. And based on that, so I will come hopefully to the finish right now. So a couple, we can even, I would say, an interesting use case, even if we have the steering system calibrated, we can then go into the next step to calibrate active lane departure warning, or in Volkswagen language, it's ASA, the cruise assist, the active cruise assist, or the lane keeping assist. And we found that, I would say, the maneuver we test and evaluate, because in our research we do a lot of evaluation methods for those other systems, and we found the maneuver can be transported, and we are now on the way to combine the steering system with a camera, for example. And then even, and the story behind is, even if the steering calibrator application engineer is ready with the steering on driving simulator, the LCAS calibrator can immediately start. In the past, if the prototype is there, they both get the prototype to do the test, but the LCAS people must wait until the steering system has a certain maturity level, and they waste a lot of time there. And what they can do right now, they can immediately start on a driving simulator with the stage of the steering calibration. And this is a task we follow. We have a big research project with Audi for that, and Continental. And therefore, I think this is will be also lead to a big efficiency. Just to give you an impression, this is an objectivation of our system. Even if you have here a center guidance, for example, and you come out of the middle line, you have a certain torque input to the driver to remain the car in center lane. You have a so-called control-free corridor, and here this is a test of overpressing, how the design of the overpressing, how the gradients, the plateau, and how you switch off the torque. And this must be designed, and this needs a long time on the road to do that. Now, with each car and with each steering, you should adapt that, and this is very time consuming. This can be done on a driving simulator. Fantastic, because it's also, I would say, straight condition. There's a certain behavior, you need a certain response, and you need a certain dynamic of the simulator. And then with a real steering system and an LCAS system, you can test that. Just one sample and makes their life much easier. And it does not mean that we don't need the test driving at all. So it's just bring you to the fact that the maturity level will increase maybe to 80%, and you have a higher level to start on the real vehicle. You are much more efficient. These are just samples. I will skip that, where we have done also benchmark with different vehicles with big subject studies, if the intervention is early, late, strong, and soft, and what does customers expect, and where it should be, and such things, such applications can be done nicely on driving simulator. And the last thing is also the comfort behavior. This is also an at the moment a key thing to answer the question. I mentioned that already. In which body motion is necessary that people can really do side jobs like reading or something in a level 3, 4, 5 cars. And what we found is that the chassis must be improved very much. I cannot go, this is it's a own research too much in detail, but so we can do a lot of blind tests with different excitation, different roll or motion axle, and also with different tasks, and ask the driver, for example, are you willing to do your working, for example, from do nothing to do everything, and which kind of working you would do by that, and from writing WhatsApp to reading WhatsApp, writing WhatsApp, reading email, writing complex email, reading reports, maybe modify reports, writing reports. So you have a different scale, and we found we have to improve the current comfort behavior of vehicles, that people really accept that, or they are really willing to do something in the car. And this is something, and then therefore we can also select which systems we need for that. No? So I think this is always the same story behind, where we can excitate people and can investigate that, then we can do some improvements, or certain system, we can qualify certain systems. And these are jobs which is more or less difficult, could be difficult done on a driving simulator. So thank you very much for your time. I'm now at the finish. And if you have any questions, don't hesitate to ask me.
Thank you, Professor Bernhard, for your insightful presentation. Now we have two questions from Mr. S. Mohan. First question, he wants to know on how can you predict 3D track model and road conditions like MUE, etc., under new roads?
Please repeat it again. I have not fully understand. How can you predict
3D track model and road conditions like MUE, etc., under new roads?
I would say the 3D track model will be scanned. There are certain companies who can do that, and will be scanned, and then will be transformed to and formatted, so-called CRG, curve regular grid, and we can run on that. On one hand, we can integrate that in CarMaker, for example, a CRG can run with a tire on the CarMaker road, but we can also run on a F tire. They have their own road, or we can run on a so-called Tata surface. You see everything in the picture. What you see here are small triangles. We can run with a tire directly on these small triangles. So a different version, and so it means this is a real digital twin. It's a copy of the real road. Is that what you is that what you ask, or is there?
Yeah. So and his follow-up question is, how can we predict driving comfort and control ADAS with different windows opening, closing under aerodynamic forces?
The driving comfort, even if you run just over such a road, and I would say we have a certain motion, and excitation of the body, and then we can excitate and move that body with low frequency and high frequency dependence on the simulation body motion, and then the driver gets the excitation. What we are doing is that we have also some sensors on seat rail, for example, that we can compare that and can evaluate that, and the excitation then would say the excitation will I think impact to the driver, and then he can evaluate that. So I think this is the first part of the question of the. And the second part was? Can you repeat the second part?
Yeah, this was the only question. So question was, how can we predict driving comfort with control ADAS with different windows opening, closing under aerodynamic forces?
Control windows opening, closing, I have not understand. Sorry.
Okay.
I would say complete different windows opening and closing, or do you mean this window, or what do you mean? I would say
it means the car windows, I mean the air coming in. So
no, this is not possible. Yeah. This was not possible. So this is not possible. So it means, I would say, for comfort evaluation, often we have also, would say, an closed cockpit. So we can also modify different cockpits for certain application. But I would say always we have to focus in our use case And here in that case, we can mainly focus on mechanical comfort, not on acoustical comfort. No? That's so it means open windows is almost not possible, no? Because you need a fan, etc. This is our own story. No? Okay. Other question? I suppose our...
Yeah, I think there are no other questions then. So...
No more questions.
No, it doesn't look like. Mr. Dipanshu, would you like to take it forward?
Thank you so much, Professor
So
Bernhard.
thank you very
No more
much.
questions. Yeah. Thank you so much for giving your time and taking those questions. There are no other questions. Now we would like to invite Mr. Raoul Popescu-Ghimis. He is the CEO and Race Software and is responsible for creating, planning, implementing, and integrating the organization direction. Raoul is an international award-winning MBS and chassis engineer with global recognition in automotive OEM and high-end motorsport world. Over to you, Mr. Raoul.
Thank you very much for the kind introduction. I will let my colleague share the screen while I'll start doing the initial bit of the presentation. So first of all, can everybody hear me well?
Yes.
Amazing. So thank you for the invitation to present today. Thank you, Ramanathan, for considering us. It's quite an honor to take part today in the Motion in Control 2021 conference. We'll give you an introduction in what our company and software capability do with some live engineering simulations. Our company is called Race Software, which comes from the Rapid Axle Concept Evolution. And we consider we are the first ones in the world to run a multi-body dynamic software in the cloud. If you like to go to the next slide, Rishi, to give a bit of, just a bit of introduction about ourselves. So as mentioned, I'm the CEO of Race Software. A bit about my background: I'm a mechanical engineer and entrepreneur with a degree in automotive and motorsport engineering and a master's in vehicle dynamics. Back in the day, I've been awarded by another multi-body dynamics company that I won't necessarily mention the name, but Professor Bernhard has mentioned it, for creating probably the world's first fully parameterizable two-wheeled vehicle model, including rider dynamics, and been awarded alongside companies such as NASA or Magna. Throughout my career, I've been involved in developing vehicle chassis and suspension systems for F1 cars, from McLaren to Red Bull as an example, and supercars such as the Aston Martin 177 or the Jaguar CX-75. I've been behind the complete chassis development for the Jaguar F-Type, but also involved in developing for Jaguar Land Rover the next generation of chassis that will probably be implemented up to 2025, including developing for them the whole four-wheel steering system. Currently, I lead the Race Software team, and I'm responsible for creating, planning, implementing, and integrating the direction of our organization. And I think that's more or less enough about myself. I shall pass it now to my colleague Hrishikesh, whom I've been working with for 13 years now. Lucky number.
Thanks, Raoul. And thanks to SA India and the organizers to invite us. And yeah, we are very excited. As Raoul said, my name is Rishi, and I'm a background is that I'm a mechanical engineer and chartered engineer with the MIMechE. So I have experience in mechanical design and engineering of vehicle components for similar kind of premium and motorsport applications across the UK, Europe, and around the world. In the recent 5 to 6 years, I would say, I have been focusing also on cloud systems, IoT, and AI functions. And this is where my role in Race Software comes in. So as Raoul said, Race Software works in the cloud, and we deploy it into users just over the browser, and making this solution work across different types of customers, different types of applications, and different types of geographies is what my role is as operating officer of Race Software. So just to set the context a little bit, I will define what the problem is that we are trying to solve, so that we all understand where we stand today and where we can go from here in terms of multi-body simulations. I'm assuming at this point the audience understands multi-body simulations and understands the overview of it, and I'm also most of you might know that it requires quite expensive hardware and software installations, which then require ongoing maintenance in terms of hardware and software licensing. So, to use the software properly, to run simulations and get the most out of the tool, you have to have engineers who are experienced with creating a model, optimizing it, and then iterating on various different options, various different setups to get the kind of the solution you would like, whether it's a sports car or a family saloon, or whatever the case may be in terms of suspension design. So this involves a lot of time, and highly experienced engineers, involves a lot of effort and cost, and there is a skills shortage, and that is those are the kind of issues that we come up with. And the solution we're trying to implement, and that we have implemented, is where we firstly take the complexity of software programming from suspension engineers and chassis engineers away. So we would like engineers to do engineering, right? Continue with optimizing the design rather than spending time on making the software work, or making adding scripts to make the software work the way you want it, or whatever the case may be. So our software is able to do this, and it's able to do this for small small teams of tier 1 suppliers, or large global OEMs with distributed teams across different continents and different markets. And the Race software, so using this, you can go from data input, which is hard points, vehicle parameters, spring loads, weights, etc. Raoul will give you a demo of this in a bit, into a fully professional suspension report for kinematics and compliance in under 60 seconds. So this is something that's been validated with other tools, and also in the real world on rigs that are available around the world, and some of the sponsors and speakers in this event make those. So what is Race software? A bit wordy here, but just simply put, we are the world's first multi-body systems cloud software package. and you can use this to develop suspensions and chassis systems. And it combines model build, parameterization, post-processing of the results and the data, storage of all of the reports, and generation, of course, of the report itself, and user management, etc., all into a single platform. So anyone can come in, create an account, put in your details, start using the tool, and Race Software has templates that are ready to go for you to start running. I'll come into templates in a minute. You don't have to perform any post-processing specifically unless you would like to take the data and run it across on other co-simulation sort of products. But otherwise, you just get the report and you have actionable insights from the report right away. We also own the IP for this for the tool itself. So we can currently we are focusing on chassis and suspension development, and that's the expertise in the team. But you can imagine it can go into like I've mentioned here, landing gear of planes, or specific maneuvers for ADAS, like Professor Bernhard was talking about, or any other mobility sort of spectrum that you can see with two-wheelers or micro-mobility, etc. So there is a little video we would like to show, just to, it'll give you a quick, within a couple of minutes, a feel of what the software looks like and what we did with Automotive Test Systems India with Mr. Ramanathan, who is in the panel here. Hello, sir. Let me bring that up. I'm hoping you can see and hear.
RACE, Rapid Axle Concept Evolution, offers the ability to go from data input to a professional suspension performance report in less than 60 seconds. So how does it work? RACE software in a standard offering only requires user inputs in the form of suspension hardpoints, joint types, and wheel or tyre dimensions. Once complete, the user submits the inputs for analysis to a bespoke encrypted cloud server. The server runs the KNC kinematics and compliance simulation and generates a report to show the performance of the suspension against over 50 key performance indicators. The report is then uploaded to the user's account for review. RACE software is the first MBS, multi-body simulation product on the market that caters for the full regulatory compliance of global OEMs, meets the high demand and precision of motorsport, offers the aftermarket industry a resellable product, while allowing individuals and tuners to develop their suspension at a fraction of the time and cost anywhere in the world on any device.
Hope that give you a little bit of a feel of what RACE software is about, what it looks like, and what the user interface is like. Just to help us understand the pros and cons a little bit better and what we bring to the table at RACE, we have the traditional antibody systems software. And we have RACE software. The challenges that additional software is that it takes a long time to set up, and it's quite expensive, very expensive really, and it requires quite powerful workstations or compute clusters on-prem, so you can use the tool to the maximum. It requires maintenance, and it requires highly specialized teams of engineers that are comfortable with both chassis systems and chassis engineering, and comfortable with scripting and a little bit of software and things. So this makes it a dual skill, which is another makes it harder for people to master. What we bring with Race is we can set up accounts and start using the tool in minutes. There's no investment. It's an ongoing subscription. If you want it this year, you can subscribe, and then next year or next month you can choose to stop if you like. Similar to other subscription tools. There's no installation. There's no software to be required to be running on your PC or Mac or tablet or phone. It'll just run on the browser. All of the data is secured in our encrypted cloud, and only you as the user have access to your data. And yeah, the cost reductions this brings is massive. We estimate 20 to 50x reductions this way. So it eliminates upfront investment as well. And you can achieve a fully validated KNC report in about 60 seconds. And we will challenge Raoul with that in a bit. And you have support from the Race software team to make any support in terms of troubleshooting or custom development. So just to give you a little bit of background on what our approach to templates, you can see on the list on the right-hand side the templates that we've got, and these are all pre-built and ready-made, so you don't have to build it from scratch and go on to all of the nuances and complexities of building up a specific McPherson strut type suspension. It's being built, so you can come in with your own hard points, your own damper and spring details and bush details and things like this to start running it. And we've chosen from our the internal team's experience, we've chosen the number of templates and the types of templates that cover a wide swathe of the production vehicle designs. And we also provide a lot of customization for each of those templates. And for our customers who require even further specific custom sort of bespoke designs, we have a number of custom templates that we develop and optimize just for their use, which is specific to them, and the design is also accessible just for them. Yeah, if you have any specific requirements, yeah, feel free to get in touch with us. Again, I mentioned the cloud bit, and just to drive home the point a little bit, the tools that multi-body simulations that require are essentially, they come in from the era of the 60s moon landing, and they've evolved massively from there. But it's still an evolution. It's not a revolution in terms of how, for example, cloud-based CAD or cloud-based FAE have gone on. But that is what we believe we are bringing in here. So you come in and start using. So the focus is on the tuning and design of the suspension and optimizing rather than the software itself. It's your design and it's your iterations that come in front and center. And that's the value add. That's what you would want to do when you're using the tool, and that's what we try and enable you to do. So it removes all of the boring setting up automations and all of the software that is required. It requires quite high amount of skill and bespoke again when you want to make changes. So I will hand you now over to Raoul. He can explain and provide a little bit of an overview of our different divisions and focus areas, and then of course give you a demo. What do you, Raoul?
Yeah, thank you very much, Rishi, for presenting everything so far. I'll just briefly touch base what we do in our company. So we have 6 different divisions, and at the core of the company is the MBS software. The SaaS, software as a service product, is a well-defined software capability with different levels of engineering that anyone can access on our platform via subscription, as Rishi mentioned earlier. We also feature an education platform, but it's the world's most used database of knowledge in this specific field. We have found that out by ranking first in Google with 0 marketing costs. In terms of engineering, we provide engineering services such as target settings, chassis concept, suspension design, virtual to physical correlation, subjective testing, but also custom MBS software development based on our IP. Due to our software efficiencies, we have been able to bring to the gaming industry a real-life physics, and we actually own a state-of-the-art driving sim model that actually helps our driver, that you can see at the bottom left of your screen, actually winning the Le Mans. We have in-house capability to benchmark chassis, but also provide to the market already benchmark vehicles that we have in-house. Finally, we run with universities, drivers, and teams programs in which we support them with our software and engineering capability, such as mentioned before, helping Tommy Foster winning the Le Mans using our capability. So that is more or less in a nutshell the 6 different divisions with our software at the core. If you like, we should to move to the next slide. And after that, I'll keep 2 live demos. So I'll be keeping you a standard level. It would be actually the model that we built with the help of the data from ATS systems. And after that, I'm also going to present you an advanced level, which basically on top of the standard level has non-linear 6 degrees of freedom bushes, anti-roll bar, and the vortex added. You can see on the right-hand side the different type of levels that are subscription-based, and you can access them within 1 or 2 minutes of creating an account, but also the custom software development that we have used, for example, to bring efficiencies into different Formula 1 teams. I'll take over now, Rishi, and I'll keep you a live demo. I think you will need Rishi to stop sharing the screen in order for me to be able to share. Thank you. Okay. Can everybody see my screen?
Yeah.
Brilliant. So for the first time that the simulation will load the basically the data from a previous simulation. So as mentioned, we'll be using exactly the Baja vehicle from the video with the data that has been supplied to us by ATS. You basically specify your hardpoint coordinates, X, Y, Z, and after that, based on our vast experience, you can basically choose the different stiffnesses at each pickup point. The standard level offering, it's like a Pareto approach 80-20. Besides being able to specify the stiffness at each pickup point, you also have full topology. So you can attach the damper to the lower control arm, upper control arm, or to the knuckle. In this case scenario, it's to the upper control arm. You can also specify your rod guide stiffness, your wheel bearing conical stiffness, and after that you enter your tuning parameters, the spring weight. For the purpose of the demonstration, I'll just change it to something else, and also the spring preload, the tire loaded radius, and the wheelbase. You press submit and run simulation, and now the data is getting securely packed, and it's sent to one of our servers, which is about 2,000 miles away from here. And the simulation is starting to run, and in about 60 seconds, we're going to get, I would say, a ready for manufacturing report. While the simulation it's running, I'm also going to present you the advanced template, and I'm going to put that simulation to run. It won't be exactly 60 seconds. It will be probably just slightly over 60 seconds, just because of the added complexity. So as mentioned in the advanced template, you also have the anti-roll bar, the roll motion test, but you can also specify each bush and it's all 6 degrees of freedom. Again, you have your XYZ coordinates, and after that you can specify your bush stiffness. So you specify your initial linear weight, for how long the linear weight it's applied to, the total travel, and the force at the total travel. So these are the parameters which you are going to use in order to generate your non-linear splines for each bush. After that, the same, you can specify your topology, where the spring is attached to, it's a coilover damper, it's attached to the chassis. You can specify your wheel bearing stiffness, the spring rate. Again, for the purposes of the demonstration, I'll just use other type of values. Your anti-roll bar rate, the tire loaded radius, and the wheelbase. We press submit and run simulation, and now again the data is getting packed and it's sent to our servers ready for simulation. As we can see, the previous simulation has already finished, so I'll be presenting you the report. You can also export the KPIs as a CSV file if you want to do further analysis or even potential for simulation. Also, if you have a CAD engineer, this is a tool that allows you to do both kinematics and compliances without going in the loop between a CAD engineer and the multi-body simulation engineer to do, design iterations. I'm going to download the report now that was generated in, in 60 seconds, the whole from input to output. And we get a 50 pages fully navigable report. The first page gives you a bit of indication about your simulation, the date, the type of suspension system that you use, and so on. The second page, it's basically a fully navigable table of contents, a statement of non-liability. Obviously, if you are going to do a flying car, it's down to you for your achievements. And after that, these are the tests that we have performed on our server. As mentioned in the standard level offering, we didn't perform the roll motion. However, all the other tests have been performed, and this would be one-to-one with KNC rigs such as the MdynamiX one. So we have on vertical motion, steering input, lateral force, braking force, traction force, tire aligning torque. After that, this is the data that we have inputted in our system. So we captured that in the report. The simulation took 53.1 seconds, so just under 60 seconds. And after that, we get the two design tables, I'll call them, with the key performance indicators. So you have everything from static geometry, steering input, vertical motion, and this would be one-to-one to an industry standard. And we also have added a few extra features because people would be interested, for example, for the bump steer, how it looks at 25 millimeters into bump. If we want to understand the full spectrum of each KPI, we just click on it and we go straight to the graph to understand the full spectrum. As we can see in this particular case scenario, the bump steer is quite non-linear, when in theory it should be improved. The second table focuses more on the compliances. You have the braking force, lateral force, traction force, and tire aligning torque. Again, everything it's backed up by graphs. So you click on one of the KPIs and you go straight away to the graph. And yeah, basically all the KPIs are backed up by graphs. And at the end of the report, you have basically the KPI sign convention, which tells you the units, tells you which is the positive, the negative metric. So that's in a nutshell the standard report. Now we are going back to see the advanced report. As we can see, the simulation has finished. So we are going to download the advanced report. So the advanced report is slightly bigger. Instead of 50 pages, it's 70 pages because it also captures the nonlinearity of the bushes and the splines presented. I won't go again through the first pages. All the tests have been completed now, including the roll motion test. Again, the data that we have inputted. And here we can see the stiffnesses for each joint that has been specified, but also the topology on the right. If we want to analyze the exact stiffness of a joint, we press on it and we go exactly and understand how the graphs look like for each degree of freedom of the 0.1 bush as an example. As I mentioned, it takes just slightly over 60 seconds. It looks that I wasn't correct. It was, again, just under 60 seconds, the whole simulation time. Maybe the server is slightly faster this morning, at least at our end, it's a bit early. As we can see to the design tables, we have the roll motion test added as well. Again, each of the KPIs is backed up by graphs. We click on one of them and we go straight away to understand the full spectrum of the analysis. On the compliances, now, for example, if we take a look at the brake steer, we can see the non-linearity of the brake steer test, which is basically induced by, the non-linearity of the bushes used in the system. All the KPIs are backed up by graphs, just like in the standard report. And at the end, again, we have basically the key performance, the sign convention, the units used. In comparison to other software from the multi-body dynamics industry, we know that for a 5-link system, we are the ones that we predict the most accurate, the steering axis with the steering, but also with our world software capability, you can also cater for 90 degrees of steering angle. So basically the wheels to be in line. I know this might sound a bit strange, but in drifting, the wheels get to 90 degrees and our software is able to capture this. I would say this is more in a nutshell how fast our capability works. If you're happy with the report, you print it and you take it for, for manufacturing or for, to the further departments to use it further. So I would say that's more or less in a nutshell what our software does. I hope it was fast enough, and thank you very much for listening. And I'm prepared to take your questions.
Thank you so much, Mr. Raoul. We have one question from S. Mohan. He wants to know, is it possible, what is the risk level of security of test data run saved in cloud app from confidentiality and time limit?
So we actually have an extensive penetration testing on our platform. We invite you all to try to hack us. And also for the high-end clients and custom clients, what we do on top is we dedicate a specific cluster on our server that they only them know about it and they can go on it. Does that answer your question?
Yeah, thank you so much, Mr. Raoul.